This is the third example of a simple collision problem that we can solve using conservation of momentum. So I still have two train cars that are going to collide. In this case, M1, this train car has a velocity, therefore a momentum to the right. This train car, M2, has a velocity to the left. So there's clearly going to be a collision here as long as there are no barriers in the way. They're still train cars. I'm going to allow them to couple up when they hit. So after the collision, I have an object that moves as one. So I can again identify this as a perfectly inelastic collision. I'll write that out. And I expect the momentum to be conserved, the kinetic energy not to be conserved. And in the previous two videos, I was pretty confident in my direction of my final velocity, but in this one, without knowing more about what these masses and velocities actually are, I'm stuck. I actually don't know what direction this thing is going to be moving. Whichever direction it is depends on which of these two objects has the greatest initial momentum. That's the one that's going to determine the direction of the final object. If the total momentum of my system is to the right before the collision, the total momentum of my system will be to the right afterwards. If the total momentum is to the left, the total momentum afterwards will be to the left. That depends on which one of these objects has the most momentum. And please remember, that doesn't only depend upon the mass. It also depends upon the velocities. I could have a really large mass with a really tiny velocity and a very small mass with a really high velocity here that will have the most momentum. But in this general form, I actually just don't know. I would need numbers. I would need more parameters to be able to handle that. But we can go through this symbolically. I'm still going to use the conservation of momentum. It's a terrible sigma. Sorry to all you Greek scholars out there. All right, momentum of the system before, it's got to equal the momentum of the system afterwards. This is one dimension. I'm going to let just the negative sign handle the direction here. So my total momentum before is M1 V1 initial minus M2 V2 initial. Again, minus because that's going to tell me that the momentum of mass 2 is to the left, whereas the momentum of mass 1 was to the right. If you want to define to the left as positive, that's fine. Flip your signs. One of them is going to be negative. That's got to equal the mass of my compound object, or composite object, if you will, V final. And I get this. V final is equal to M1 V1 initial minus M2 V2 initial over M1 plus M2. Notice what we can say here is the final velocity, because of this negative sign, is going to be somewhere between these two velocities. It's going to be, whichever one is fastest, it will be slower than that. Whichever one is smallest, it will be faster than that. It will be somewhere between these two because of how this negative sign is going to interplay with our values. But until you have numbers, this is as far as we can go. But conceptually, it's very, very important to be able to get here.